Welcome to the Insightful Professor. Today's topic is creating a table in Oracle database. In this tutorial, we will present the basics of creating a database table in an Oracle database. Much of what we're going to talk about will be applicable to other relational systems as well, such as SQL Server or DB2, but the syntax for data definition statements tends to be very specific to a particular vendor because some of the data types might be different and some of the features might be different. And again, we're going to be illustrating the concepts using Oracle database. But again, the concepts should extend or apply to other commercial products. So what we're going to do is present a couple of examples to reinforce the concept that we discussed. And then we'll show something pretty neat, how you can take a bunch of commands that have been predefined in a text file called a script, and how to actually execute those commands, that is, how to run a script. So rather than enter the commands for each table one at a time, what we'll do is put all of the commands within a file and then run that script. So we have a script available, and we'll show you what's in there, and we'll show you how to run that. So what is a database table? Well, you should be comfortable with this by now, assuming you've watched some of the other videos. A table is simply a collection of columns, each of which has been given a name, and a collection of rows. And the rows have no name, and they have no order imposed on them. So a table is a representation of something in the real world that we would call an entity, more specifically an entity type, kind of like the idea of a class in object-oriented programming. So we would have something like a department table, an employee table, a vehicle table, and so forth. These would all be different kinds of things that exist within our application domain that we're trying to represent within the system. Now, each row in a table corresponds to one instance of whatever that entity type is. So if we have an entity type for department, each row then would represent one particular department. Similarly, for employee, each row would correspond to one employee within the organization. Each column in the table corresponds to some attribute or property or characteristic of an entity, and given a column value taken from one row, we're saying that what we have is the value of that attribute for one particular instance, such as, for example, the date of birth for a particular employee named Mo. So each column is given a name and is said to hold or store data of one particular type or some data type. And that's going to be specified when we create the table, what kind of data will be contained within the column. So the data type determines not only what values are permitted in that particular column, but also what operations can be performed. For example, if we have a numeric column, it may make sense to do arithmetic with the values. But if we have a character column, doing arithmetic doesn't make any sense. So when a table is created, there are rules or constraints that might exist within the real world, constraining the behavior of that entity type. And we want to be able to reflect that kind of behavior within our database. So we can define these rules or constraints which will influence or affect the content of the columns within some row, or even a row being able to participate in a relationship. When we add these types of integrity constraints as part of the create table or data definition statement, these are called declarative integrity constraints. So, what data types are available in Oracle database? Well, we haven't exhausted the list, but we're giving you a few of them here. What we're showing is a partial list that shows us, first off, what we'll call character data. So we have char and varchar or varchar2. These would be our two primary character data types, where we can store strings of characters, like a person's name, for example. We also have a variety of numeric data types. Oracle's primary data type is number, but they also support binary float and binary double, which adhere to the IEEE 754 standard, which is the same standard that you'll see defining things like Java's numeric data type for floating points, or XML's data types. So that's pretty neat, because that means you can store data from these other systems within Oracle and then retrieve the values, and you'll get the same value out when you retrieve that you put in. You're not going to lose some of the precision or accuracy. In addition, there are chronological data types like date and timestamp. Oracle has other data types, but these are the primary data types that will be of interest to us in this video. Let's get back to the integrity constraints. These correspond to what we'll call business rules that define the behavior or govern the behavior of these real-world objects that we're trying to represent within a database. So these might have been discovered as we did data modeling, as we develop a logical data model, which is a representation of the application domain or problem domain. We discovered certain things about the behavior of these real-world objects that we want to somehow capture and implement within our representation, hence within the database. So some of the integrity constraints can be defined declaratively. Again, what that means is it's just an extension to the create table statement. These would be things like not null, unique, check, primary key, and foreign key. The integrity constraints, again, correspond to real-world, say, functionality, and sometimes these integrity constraints can be quite complex. And if they're more complex than a simple statement of fact, such as not null, effectively meaning the column's value is required, but it's more complex than that, then we might have to describe some kind of procedure or process that has to be followed, kind of programmatic implementation of an integrity constraint. And this can be accomplished within a database such as Oracle, or DB2, or SQL Server, using something called a database trigger. We're not going to get into that now because that's above and beyond what we have time to talk about, and that also requires understanding some kind of a programming language such as PL/SQL in Oracle. Now, back to the integrity constraints. We listed them. Let's explain what these things mean. We have a concept of what's called entity integrity implemented through what's called a primary key. So each table can have a single primary key. Now that primary key need not consist of only one column of data. It could consist of multiple columns. In fact, Oracle allows up to 32 columns to be defined for the primary key. But the point is, a table can have only one such key. That key could be a single column, atomic, or could be multiple columns, composite. This serves as the unique identifier. It corresponds to the real-world behavior, where if we say, for example, each employee must be distinguishable in some way from other employees, and what we do is say something like, the employee's badge number is unique. No two employees have the same value for that, then that column could very well serve as the primary key. But in order to serve as the primary key, the first thing that we just mentioned is it must exhibit this uniqueness property. Whatever the value is must clearly identify only one and no more than one entity instances or no more than one row in our table. But the other property is it can't be optional. It's a required field. It cannot be null. So for example, if we're dealing with employees in a company, every employee presumably must have a badge and hence a badge number. So it can't be null. And that badge number serves to uniquely identify one employee, distinguish them from all the others. Based on that, the idea is that the badge number could qualify as the primary key. And as we said, it could be a single column, atomic, or it can be multiple columns, composite. Oracle, like some other databases such as SQL Server and say DB2 for Linux, Unix, and Windows, will automatically create a unique index on the columns that you've designated as being the primary key. The name that is given to the index by default would be the name of the constraint. And that's kind of an important point to note if you're going to be doing database administration. If you're just a user of the database or a programmer working with the data, that may not be that important to you. But for database administrators, it becomes significant. The other integrity constraint tied to the primary key is something called a foreign key, whereas the primary key implements a feature called entity integrity. A foreign key implements something called referential integrity. And referential integrity refers to the concept of a row, typically in one table, referring to a row in typically a different table. And this is how we capture relationships within the relational database. So a foreign key also includes something called a delete rule that indicates how the system should respond if you attempt to delete what's called a row in the parent table when there are children, rows that contain the foreign key that make a reference to that row. Hopefully that'll become a bit clearer in a moment as we look at an example. So Oracle supports the following delete rules. We would say on delete cascade. We could say on delete set null. Or if we're silent on the point, then the implied rule is on delete restrict. What does this mean? When we have cascade, we have a parent row. Say that would be a row in the department table. And we have a child row, a row in the employee table. The relationship that we're depicting here would be an employee works in or an employee is assigned to some department, which means that a row from the employee table would somehow be associated with, by making a reference to, a row in the department table. And that's where we get the relationship of the child and the parent. The child in this case would be the employee table, and hence the employee row, and the parent would be the row being referenced, and that would be a row within the department table. So the idea here, going back to this brief description of referential integrity, would be what happens if you try to delete a department which currently has employees who work in the department, hence employees rows who are referencing the row you're trying to delete from the department table. That's where the delete rule comes into play. So if you attempt to delete a department which currently has employees, and the rule for the referential integrity constraint, or for the foreign key, said on delete cascade, this would allow the deletion of the parent row. The department can go away, but also the kids, the children go away. Those employees would no longer exist within the employee table. So the cascading delete is not too good, I guess, if you're the employee assigned to a department that's being removed, if the company's doing downsizing. Now, if you had on delete set null or nullify, then if you attempt to delete the parent and there are currently children, that is, there are employees assigned to that department, you would be able to successfully delete the row from the department table. But the children, the employees in the employee table, those rows would be preserved. However, the foreign key, which had previously identified the department being deleted, would now be set to null, making these children effectively orphans, saying that they are no longer assigned to any department. And the third option is the restrict. Here what happens is if you attempt to delete a parent row, and there's at least one child that references that row, the deletion against the parent would fail. It would be rejected by the system. That's the concept of referential integrity, kind of from the child to parent relationship there. So here's the create table syntax. This is the basic syntax. It's enough to get you going, but it's not comprehensive. It doesn't cover all of the aspects of creating a database table. So obviously its purpose is to define a database table. In order to execute this command, you need a privilege, a system privilege called create table. And you also need authorization to use some disk space, what's called a quota on a target table space. So this particular form is a simplified form of the create table. You give a name to the table, and then within parentheses, you specify the name of each column, the data type of the column, and optionally one of these declarative constraints we talked about, such as not null or primary key. Additionally, constraints can be specified in a different way using what's called a table constraint. It's just an alternative variation on the syntax. In some cases, the only way that you can declare a particular constraint is by using a table constraint, so it is important to know both forms of the syntax. Here are a couple of quick examples. We're going to create the department table, And the department table has as a primary key this column called DEPT, which is a variable length character string of 4 characters max. The primary key is designated as being associated with a constraint called PK department. And then we create a table called course. The course table also has a primary key, CNO. No two courses can have the same course number or value in the CNO column. Additionally, we have a relationship between the two tables. The relationship is captured here with CDEPT making a reference back to the department table DEPT column, which is, as we know, the primary key of that table. A couple of important points. DEPT as the primary key in department is called varchar2 length of 4. CDEPT, what we're designating as the foreign key in the course table, has to be the same exact data type and same size. But observe that the column names don't have to be the same. Very often they are going to be different. But the data type and size of each must be identical. Additionally, we're referring back to DEPT, which is the primary key. The other point about all of this is that department plays the role of the parent, course will play the role of the child in this parent-child relationship. It's important that the department table be created or defined first, and then the child table can be brought into existence. This is important because the system has to validate that C department has the same data type and size as the primary key of this table. If the department table has not yet been created, the system cannot validate the foreign key, hence the create statement of course would fail if the department table had not yet been defined. So we have to define them in a particular order. Let's take a look at this in action, and what we'll do is get ready to go to the database, but before that I want to give you a little heads up on some of the metadata. When we create a table, the table definition is going to be recorded, or the table's existence will be recorded within the database in the system catalog. And we could look in something called user tables to look at the tables that we own. There are some other views as well to look at tables that other individuals may own, but we're permitted to access. So we can query what's the table name of any table that I own, and we will get a list of those tables, assuming we own them. Additionally, when constraints are declared, there's a column in user constraints, and likewise there's some other columns for other tables owned by other individuals, but this is for tables owned by the current user. These are constraints on those tables. You'll get the name of the constraint. Additionally, you'll get information about what kind of constraint. We're showing you the 4 primary types of constraints of interest to us here. P would be the value and constraint type if the constraint that we're identifying is a primary key. R would be the value and constraint type if the constraint is a foreign key. C if it's a check constraint. And by the way, not null is just a special variety of check constraint. U if it was a unique constraint. And here we're narrowing it down to the constraints that apply to just one of the tables, department. Remember, we're going to be looking at these 2 tables here, department and course, and then we're going to check some of the metadata to see how things came out. Now, before I overload you on the metadata, let's go and try this stuff out. Okay, I'm connected as student, and this is a user that we created previously. So we have a student user, and the student has authority to create a table and so forth. Let me show you how we can find that out. The commands that I'm going to execute here will be available in the script that I'm posting online after the video. So here we're going to try it out and say, what is the target table space, my default table space? Should I create a table and not say where to put the table? What is my default table space? And the system says app data. And again, in earlier videos, we created this table space and associated it with the user. So that's where the system will try to put the data in terms of the storage, where it will come from. Now, let's take a look. How much room do I have? What's the quota? For any table space, you have to have authority to use some of the storage. So what I want to do here is see how much storage I'm permitted to use within a table space called app data. And here's another view called user TS quotas. I fire this up, and it's kind of frightening. You probably jump back at the moment. It's -1. I can't use anything? And what's a negative number? Well, what happens is when you have unlimited amount of storage, an unlimited quota, it comes out as -1. So it's actually a good thing to see this negative number, not a bad thing. Now, that means we've got plenty of room, provided there's plenty of room in the table space. Here's the create table statement for the department. This is for the parent. Let's go ahead. Here it is, and I'm going to fire it up and create it, and it says the table was created. So that's good news. So now we have the parent and we have a primary key. Let's look at creating the course table. I'm going to grab this guy, and this guy, remember, is the child in our relationship here. It has a primary key, but it also has this foreign key that refers back to the other table. So the tables were created according to our acknowledgement here in this feedback statement, but it would be kind of nice to get a little bit more confirmation that everything went well. We can do this by examining some of the metadata. So let's run this query to identify all of the tables that I currently own, all of the tables in my schema. And that's good news. We see department and course are both listed as tables in my schema or tables that I own. So this statement that said table created, it seemed to be accurate. Now, we're going to check out some of the integrity constraints. Remember, I said P, R, C, and U would indicate a primary key, a foreign key, or a reference constraint, a check constraint, which would include not null, or a unique constraint. Here's how we can find this out. I'm going to query this table called user constraints and find out what is the name of the constraint and what kind of constraint is it for the department table. Let's see if we have any constraints in there. Remember, we defined a primary key, so we should see something, and sure enough, here it is. The name of the constraint is PK_DEPT, and the type is P, indicating primary key. Scroll back for just a little bit, and notice that's exactly the name we gave to the primary key constraint. So that looks like it's working great as well. Now, suppose you kind of bump into a constraint like that. You're walking down the street, and all of a sudden you bump into a constraint that claims to be the primary key constraint of a table. Wouldn't it be nice to find out what column or columns make up that primary key? I think it would be, so I'm going to show you how to do that here. I'm going to take this additional query and fire this up, and I actually made a mistake in what I ran here, so we'll fix it. I'm selecting the column name and the position from user_cons column, where the name of the table is department, and the constraint name is, well, that's not the name of the constraint. We just saw it was PK department. So let me quickly remedy this little situation, and we'll simply call it PK depth. And now we fire it up, and we see that there is a column in the department table, and there's only one of these, so its position left to right is position 1. But DEPT is the name of the column that happens to be or is the only column in the constraint called PK department. We'll back up here, take a look. Sure enough, that's the column that made up the primary key. Boy, this is getting really exciting. I have to pause and take a deep breath. I'm sure you do as well. Okay, I think I'm ready to go on. Okay. Here's another interesting one. What about referential integrity? I'm going to look for the constraint in the course table. Remember, we had noted this was the child in the relationship. I'm going to look for the constraint in the course table that is of type R, find out what its name is, and then there's an R constraint name, which is going to be the reference constraint. Remember, a primary key is going to be the target of a foreign key reference. So that's what the R constraint is going to give us, the name of the primary key constraint that our current reference constraint is pointing to. And we'll also see what the delete rule is. And I'm doing this for the course table. And what do we find? The name of the constraint is FKC department. Scroll back for a moment through the course table, and FKC department identified the foreign key. Okay, and notice that it references the depth column in the department table. Remember, that's the primary key in the department table. And what was the name of that constraint? The name of that constraint was PK department. And here's where it all comes together. What we have is the reference constraint. The thing that this foreign key is kind of bound to or associated with is called PK depth. The delete rule is no action. That happens to be the way Oracle records in the metadata on delete restrict. So if you attempt to delete a row in the parent, attempt to delete a row in department, and there are currently one or more rows in the course table that make a reference to that, no action will be taken when you attempt to delete the parent row. That's how Oracle states on delete restrict. Anyway, kind of funny terminology. Everybody uses something a little bit different, but the concepts hopefully are very clear to you now. Okay, we've done quite a bit. Let's go back here and take a look at what's going on. We've talked about this. Now, let's look at a little bit more metadata. We already talked about this and we ran it. This is how we identify the columns over which a constraint is enforced. And then how do we identify the foreign key constraints for a table? That's where we're using the type equal to R. Both of these commands are within the script that I'm posting, but hopefully now, having seen them run, this makes more sense to you. Now, say we're all done with those tables. We want to get rid of them. I know we haven't done anything with them. We created them. But I've got a little idea here. I want to show you how to run a script. So before we do that, we want to get rid of these tables. To get rid of the tables, I'm going to drop the child, which is course, and then I'm going to drop the parent, which is department. And then we'll review what tables we have. So let's go back into our database and take a peek at this. And I think I've got the commands ready to go here. Okay, I'm going to drop the course table. And that slides right out. It's gone. And we'll confirm that in just a moment. Drop the department table, the parent, and that goes away quickly as well. And now, what tables do we own? Well, we're right back to where we were before the video started. We have no tables. But don't be alarmed. I'm going to show you how to run a script and create a whole bunch of them all at once, rather than doing it one command at a time yourself. So now let's go back to the presentation and see how we're going to do this. First off, what is a script? We had mentioned briefly in the introduction that a script is basically a series of commands contained within some kind of a text file. And what we're going to be able to do is to say to the system, to our front-end tool, run all of the commands in this script or in this file one after another, in the order in which I've listed them or the order in which they appear within the file. So each command then will have to be terminated with a semicolon. The semicolon is not part of SQL syntax, but essentially it's a separator to be placed between commands. So I'm going to say create this table, semicolon. Create this other table, semicolon, and then do a whole bunch of things, but I need to separate the commands. That's the semicolon, kind of extended syntax, not really part of SQL, but allowing the front-end tool to distinguish between the multiple commands. So to run the commands, we're simply going to tell the front-end tool to say, hey, run this script. We'll tell the front-end tool where the script is located so it knows where to find it, and then what we'll do is simply let it go through those commands one by one. So these commands often are bundled together in a script for maintenance scripts or sometimes for distribution by developers. So software developers and vendors will often use scripts to accomplish tasks. And then when a database has been installed, maintenance, for example, like on a regular basis, go out and collect database statistics, you might do a bunch of commands within a script to accomplish that. So they simplify the task for people by predefining these commands, and they kind of standardize how the task is going to be accomplished. So there's a lot of useful application that comes with scripts. So we're going to look at the same command tool, SQL+, that character command prompt. And the way we can execute a script is by using the @ sign and put it before the file name. The file name is assumed to have an extension of .sql. Alternatively, the start keyword can be used, and in that case, there would be a space between start and the name of the file. Now, the name of the file can include a drive, such as the C drive, and some folder where the file might reside. And this could be a complex path going within a folder, within a folder, within a folder, and so forth. So you're basically given the location of where the script resides and then the name of the script. And all of this would be entered right after the command prompt, which by default is SQL greater than. Keep in mind that the way you would enter the name of the command is dependent upon the operating system you're using. If you're using Windows, then it's not case sensitive. If you were using Unix or Linux, a case-sensitive operating system, then you would have to spell SQL exactly as it appears in the operating system. You would also have to spell academic.sql exactly as it appears in the operating system. Because effectively, the front-end tool of SQL+ is going to be communicating with the operating system and must coordinate the case sensitivity or insensitivity, as it may be, for the operating system file name. So let's give it a try. I have exactly what you saw there, a folder on the C drive in a location called SQL. And within that, there's a file called academic.sql. Now, we're going to hit enter, excuse me, and things are going to happen. Notice you're getting feedback. Did this, did this, did this. One by one, it's doing the commands. Let's take a look at what's in the file. Okay, here's the file that I just ran. It changed the session. That's not that important to understand. It's just changing the way the character string that I have for date is going to be interpreted. Then it created the department table, put rows into the department table, committed those rows, created the course table. Then it proceeded to insert rows, commit the change, and step by step it went through all of these operations, creating a whole bunch of tables for me. Again, this file is available on the website as well. Well, with all of that, let's see what happened. We saw the result, but let's see if all the tables are there. We have 10 tables. That is pretty exciting. So whoever wrote the script, a real nice guy, put all the commands to create the tables, populate them, and so forth. So now we have a whole bunch of tables out there, and now we can proceed to go into the SQL videos that we have and run queries like select everything from the course table. We're in good shape at this point. So that is the idea of creating a table and simplifying the task by actually running a script. So the files that I've described are available on the website, www.timhartley.com. Go to that website. There'll be a link in the menu for the Insightful Professor. Go there and you'll find the academic.sql. You'll also find creating a table, which has all of the commands that I actually ran here. And additionally, if you want to remove all of the tables, there's a script called cleanup.sql. So I hope you found this to be informative. Yeah, I know it was interesting. I really got excited about it. And if you agree, please offer some comments. And also consider subscribing to the channel to show your kind of vote of confidence or support for what we're doing here. Again, there's no cost for that. It's just kind of like following someone on Facebook. You're just showing support for us. And once again, thanks for watching.